Okay, last video of the semester. Alright, so this video we're going to be talking about the fundamental theorems of calculus, or theorem, parts 1 and 2. And I'm going to give you time to read this while I'm talking, but really, part 1 is the big crux of this theorem. Right? And what does part 1 say? It really just says when you take the derivative of the integral, you get back your original function. And that really emphasizes the other name of the integral, which is the antiderivative. That's really what this is about. And this is kind of like a cool corollary that we have to calculate integrals, definite integrals. Okay. There should be about enough time to read that. Okay, now here's a little thought problem that I don't have a written solution to, but it's just something to get you thinking. This is a historical problem that a lot of people who did a lot of calculus back in the day, before it was named calculus, this is kind of a version of integration that they were doing without thinking about it. And really, it's when you want to travel anywhere from island to island or mainland to mainland or anywhere across the world, you couldn't fly because planes weren't invented, so you had to go by boat. And one of the big problems that you had to face if you were a traveler by boat, a sailor of some kind, you had to figure out how much stuff can you fit in your boat, right? These boxes of this size, these boxes of this size, some boxes are smaller, right? Other boxes are like weirdly shaped, right? Other boxes aren't boxes at all, they're more like bags, right? So they're even more misshapen. And so you had to figure out, right? You had to work with your team and kind of figure out, how do I fit all this stuff in here? How do I Jenga this stuff in here? Right? And one way to figure out approximately how much stuff you could fit is to calculate the volume of your boat. Right? How much stuff can I fit in here? Right? Or if you had a raft, right? You had to figure out how much space was on your raft. And that was like an area function. Right? And so we were kind of adding little shapes up. And before we knew it, we were doing integration. It wasn't called integration. It was more like calculating volumes. But the Babylonians did it, the Chinese did it. Pretty much every semi-developed civilization has done it at some point. And so they all did some form of numerical integration. And some people got really curious, right? They noticed that the smaller I make our hypothetical boxes here, the better these boxes kind of fit along the curves of whatever we're adding up against, right? And so we can go all the way into the niche corners of the boat, and if the box is small enough, it fits. And it's really weird. They were kind of weirded out that some curves could fit so perfectly given something so small that was, somewhat more sharp than the curve. Obviously, a box is not curvy. Okay. So you had some intuitions and suspicions about integration back in the day. And there is some people who systematized that type of knowledge and people who wrote it down. Um, there were different schools that wrote it down and published books on it. And one person who studied these books was a guy by the name of Isaac Barrows. And Barrows had a very curious student who wrote on the idea of fluxions and rates of change and anti-fluxions. And that student's name was Isaac Newton. And at the time that they were writing about this calculus, if you so much as whispered about this idea of infinities, you could be jailed. You could be killed. Because to talk about infinity would be to talk about God, and God is not touchable. Right? You can't reach him. And so to try and reach him with math was like, no, don't do that. And so for a long time, calculus and research into calculus was held back somewhat. But it was really pushed forward by leaders like Napoleon, who hired different mathematicians and engineers to calculate projectile motion and fluid dynamics and thermodynamics and things like that. And so it really moved calculus along the applied sciences until we got to mathematicians like Euler, who systematized and published a lot of books and popularized a lot of notation that forerunners like Newton and Leibniz had written down for the first time. And then we reach Cantor and Heine, who talked about countable infinities and things like that. And people who systematize the axiom of choice. But that's just a whole overview of things to look up when it comes to calculus. There was no original problem, per se. But this is a common problem way back in the day. I think I've spent more than enough time on history. But anyways, so these are the theorems we're going to use in the proof. Don't worry too much about like memorizing them. I'm going to mention them as I use them. So, but I'm just going to scroll through, and I'm going to really quickly mark this. This is really important. This is also really important. These are kind of given because we're taking derivatives and integrals, so we kind of need continuous functions, or for functions to be continuous. These are all really important. Yeah, don't worry about it too much, but these are the theorems that we're going to be using. Okay, moving on. So the fundamental theorem of calculus, part 1. What are we saying? Okay, so for starters, we have a function on an interval being mapped into the real numbers. It has an inverse, is really what this is saying, and it's continuous on our domain, right? Okay, and then we have this thing right here. This is, some people like to call this the accumulating area function, and what it looks like, I'm gonna switch screens here. What it looks like is if I had a function, right? If I had a function, and this is sine that's being approximated here, and I move by the value h, it gives me the total area up to h. That's really what's going on here. That's what that looks like. So there's your little animation. But anyways, that's this function right here. So basically, you give me an endpoint, I give you an area under the curve. Right? And what another thing we need is x needs to be within our domain, but also that's kind of intuitive. We kind of need that to happen. So now we're going to pick an h, a real number h, where when we add x and h together, we get another number in our domain. Okay, so we've covered all of our givens. Okay. So since this is a function, right, just like any other function, it has a difference quotient. It's this, right? Notice how, like, it's missing the limit. If we wanted to make this a derivative, we'd have to take a limit, and we have to show that this limit equals some kind of value, some kind of constant, or whatever value. So let's see what happens. Let's take the limit of the difference quotient as h approaches 0. That's this. Okay, we need to simplify it. So we can pull this h out like this, and we can distribute the limit notation like this. Okay, from our accumulating area function definition, this is going to be our endpoint, so this is our argument, and this is where our argument goes in the definition. Same over here, that's where our argument value goes. We kept our negative sign, and we kept that 1 over h. What we're going to do now is we're going to swap the bounds of the integration. And essentially what we're doing is we're adding up each of the pieces that we're doing in the accumulating area function. We're adding up in the other direction, so we get a negative value. And that's why we multiply by a negative, to reflect that. So now we have a negative and a negative, and we have the end point of this sum is the start point of that sum. So what we're going to do is going to pull that negative out. It's going to go over here. And we're going to merge these two integrals together like that. So now this start point goes over here, and this end point goes over here. And this t, if you're really concerned about it, because we're integrating, where does t come from? T is just a dummy variable. Don't worry about it. We're really worried about x. So now we're going to bring that negative back into view. And the reason why we're doing that is so we can make it nicer by swapping the bounds of integration again, multiplying by a negative. Negative times a negative is a positive. Okay. And then there's our little stopping point. And then to continue, let me just zoom out really quick. To continue, we're going to do a little, we're going to talk about the mean value theorem. Now, the mean, what is a mean? Well, that's just an average. That's really what the mean is. What's an average? Well, we take the average of a bunch of values by adding them up, right? And then we divide by the number of values that we have, right? But this is only for the finite number of values. What about if I had an infinite number of values between two numbers, because we're on the real numbers axis, right? Well, that looks kind of like this. And the way we interpret this is we're taking a sum, because that's what an integral is. It's a sum. And we're evaluating all of our values by f, right? All the x values between a and b, we're evaluating into f, our function. And we're dividing by the distance, the positive distance between a and b, where a and b, or where a is less than b. So that's a positive distance. And in a sense, that's the number of values that we have, which is the distance between a and b. And what does that look like? That looks kind of like we have a start point A and an end point B, right? We're gonna take f of this point right here, f of that point right there, and so on and so forth all the way across till we get to B, starting from A. And we're going to add up all those f values. And then we're going to divide by B minus A. And that's what we're doing here. So the distance here is B minus A, because A is less than B. And what we're doing here is, since we're taking an integral, how do we take an integral? We take it like this. And we take it from the start point to the end point with our function with respect to x. And so that's our aside right here, like our little refresher of what averages mean and what is the mean value theorem. What is the mean value theorem really saying? Well, that just means that there's some point in C within AB where if I take f of C, I get that average function that we just talked about. I get this number here. That's a constant number. And that constant number is this. And what does that really say? Well, the way we use that for this particular expression, we use it like this. So we note that our start point, that's x. Our end point, that's x plus h. So the distance between our start and end point, b minus a, is x plus h minus x, which is just h. And so that's 1 over h. Boom. Okay. And there is a c between x and x plus h, where if I take f of c, I get our operand of our limit. Okay, and that really all just means that we can plug in f of c in the place of our operand here, the place of our integral. Just so I don't repeat myself. So, since I can say that this comes out to be a value, right? So f of c, it doesn't depend on h anymore. So this is really just f of c. Boom, done. And since that exists, we can call this the derivative. Remember how I mentioned that earlier? So now we can say this derivative actually exists because it comes out to be an actual value, right? But here's something else. C, it's between x and x plus h. And this interval here, it's shrinking because we're taking the limit as h approaches 0. So since it's between x and x plus h, when we take the limit as h approaches 0 of everybody, c kind of snaps into place. And so it's both less than or equal to and greater than or equal to x. And the only way that's true is if c was x. So really, this is equal to f of c, which is really equal to f of x. And so, at the end of the day, we said this derivative exists because this limit exists because it comes out to be a value. And so therefore, the derivative of the antiderivative, or the accumulating area function, is our original function for all x in that interval. Proof done. Yay. Right? That was part 1 of the proof. And really what this means is the rate of change of this area function is our original function. And if I add it up in the same way, if I add it up with increasingly small widths under the curve, under this curve, I would get our capital F of x. So if I take the derivative here, I get this. If I take the integral of this, I get this. That's really what this theorem says. Now, here's another cool aside. Since capital F is differentiable, it's also continuous on the interval, including within the right side, this side of A, and this side of B. So if we sent a sequence as h approaches 0 from the right for A, we would get f of A on the right side. And that f of A on the right side, that's actually capital F prime of A on the right side. And same for this B, right? This is actually f of B from the left side if we're approaching from the left, right? And that's actually capital F prime of B from the left side. And this is kind of like a c value somewhere between x and x plus h, where h is some kind of increase from x. And really, differentiability implies continuity really just means on a continuous curve, right? If this curve, if I can take the derivative of this curve, it has to be continuous. All right. And this is just a refresher if you want to take the time to read it. That's why I'm talking extra. This is just a refresher of what continuous actually means, the technical definition. Okay. So that's the end of part 1 proof. Let's talk about FTC2. So what is FTC2? Well, if f is continuous on our domain, and f is any antiderivative, just like how we said earlier, of f on that domain, then we have this little equation here. I'm going to talk about what this equation means and why it's useful. Okay, so remember our givens from our proof for FTC1? That's the same givens. But now we're going to tack on an extra one. Now we're going to define this function g of x to be this function, f of x, plus some constant c. And this constant c, when we take the derivative of both sides, so if we say g prime, that's going to be equal to f prime. And then c, that goes to 0 because we differentiate. So the derivative of a constant is 0, right? And really, that's what f is. And c, again, it gets eliminated by differentiation. Eliminated. And we really, really want to stress that this kind of antiderivative, right, this general antiderivative, it really exists because of that relationship where if I take the derivative of an integral or the derivative of the antiderivative, I get back my original function. Okay, now let's talk about the difference between g of b and g of a. So g of our endpoint minus g of our start point. And what does that value look like? What does that difference look like? Well, we can plug in that, we can recognize that g of b, that's just f of b plus c. And g of a, that's just f of a, right? That's just f of a plus c by substitution, right? And we can distribute this negative to the c, so that's a plus c, that's a minus c. Those c's cancel out. And so we're left with f of b minus f of a. And what is f of b? F of b, if we remember correctly, right? That's the argument, that's our endpoint, right? So there's our dummy variable. That's what that definition of f of b is, right? Because for f of x. And same for f of a. That's what f of a is. But here's something special. If our start point is exactly equal to our endpoint, there is no b minus a. There's no width to calculate. So there's no area under the curve to calculate. Right? And so this piece right here, this area, is actually 0. It's gone. And so really what we're left with is this right here. And so what did we start with? We started with our antiderivative. And no, it's not exactly the same, but actually, it is exactly the same because of this f of b minus f of a. And so f of b minus f of a, that's actually this. And if we want to calculate this, a shortcut, a way to think of it, an alternative shortcut to this, because this, right, what was the definition of this? It's this. It's this big sum that we have to calculate for every point. So if you don't want to calculate that and f is continuous, you're more than welcome to just take the antiderivative of f for the start and the end point of your interval. And there you go. That's the shortcut of a definite integral. That's FTC2. Now, there's some other cool corollaries to the fundamental theorem of calculus, parts 1 and 2. Let's take a look at them. So, this is one that's often applied. It's applied in physics. It's applied in projectile motion. It's applied in a lot of different ways because of the relationship between acceleration and velocity and position, displacement. And what is this right here? Well, in the fundamental theorem of calculus part 1, we took the derivative of an integral, right? But here we're taking the integral of a derivative. And in actuality, this is like parts 1 and 2. Parts 1 and 2 at the same time, because this is part 2, and this is kind of part 1. It's a different version. And so this is like a cool little coincidence. This is called the net change theorem. And the net change of a differentiable function over an interval. And so really, if I had a spatial function or some kind of position function s prime, that's v, that's velocity. And velocity, the rate of change of velocity, that's acceleration. That's the whole point of FTC1, right? That's that whole relationship, is that there's a function. When I differentiate it, I get the derivative, right? If I took the integral of it, I get back our positional function. And same with acceleration. If I integrated acceleration, that's our velocity. If I differentiated velocity, that's acceleration. Okay, that's pretty cool. So here's like a little bit more abstract way to think about FTC 1 and 2, a corollary. It's called Leibniz's rule. And I think I mentioned Leibniz, I name dropped him earlier in the video. But Leibniz was another precursor, forerunner to modern calculus. He was a huge fanboy of Newton, actually. When he sent Newton the Renaissance era equivalent of an email called a letter, he sent him all this stuff. He's like, hey, Newton, I've been reading your work. I'm a huge fan. Here's some cool notation and stuff I did with your work. And Newton read it, and he was very, very paranoid, because if he published anything like that, he would get jailed, like I mentioned earlier. He'd get jailed, or he'd go to asylum or something like that. But if he didn't publish, then someone else along the road would publish the same work, or essentially the same work, and they'd get credit for what he had already discovered in the same era. And so he's very, very paranoid of people publishing before him. So when he saw Leibniz's work, he was like, oh, you're an imposter. You're a fraud. You've been copying me. And Leibniz was just a fanboy. He was a traveling a lawyer. But that's one of the big reasons why Newton and Leibniz never really collaborated, even though to some degree they did. But anyways, this is Leibniz's rule. When I take the derivative of an integral of a function, where now the bounds are actually some kind of functions of x. And so I'm actually calculating the area between two functions. And so when I take the derivative of that area function, I get this weird looking thing. And the way to prove it is actually you use FTC2. They don't use it outright. They don't quote it, but they're using FTC2. And how do I know? Because if these are the bounds, look what we're evaluating. That's just our B, and that's just our A. Really cool stuff. And then what we're going to do to get that derivative, we're going to differentiate both sides with respect to x. And then we can use stuff like the chain rule, which I assume you know. And then that just gets back what we wanted to prove. So a really, really cool corollary, in my opinion, is Leibniz's rule. And then that's the end of that video. It's almost exactly 30 minutes. Hopefully I didn't cover things too fast. But yeah. Hope you liked it. Waiting for your feedback. It's been a cool semester. See you guys around.